Now we will see about extrinsic semiconductor. As I said earlier, we have two types of the extrinsic semiconductors. One is N type, second one is P type. Okay. So here, by using the concept of doping, this doping is very important. Doping. Using the concept of doping, we can create these extrinsic semiconductors. Whether it is N-type semiconductor or P-type semiconductor, we can able to create them using the concept of doping. So you have to take pure semiconductors only, and then you need to add the impurities, or you need to perform the this doping process on the intrinsic semiconductors. So then these extrinsic semiconductors will be created. So what is the exact meaning of the doping is nothing but addition of impurities. Simply, what is doping? Means addition of impurities to intrinsic semiconductors. Addition of impurities to intrinsic semiconductors, so then you will get extrinsic semiconductors. So the addition itself is called doping. So, for example, there is a device which can perform the doping process. Okay, that means for the intrinsic semiconductors, if you apply doping, you will get here extrinsic semiconductors. But doping is involving addition of impurities. That impurities can be third group impurities, or impurities can be fifth group impurities. Okay, so if you take third group impurities, what will you get? Or if you take fifth group impurities, what will you get? That is what we need to see. So if you apply this intrinsic semiconductors to third group impurities, then whatever the extrinsic semiconductors you are getting, those are N P type. P type extrinsic semiconductors you will get. If you take intrinsic semiconductors under the doping process of addition of the fifth group impurities, then you will get N type extrinsic semiconductor. These are very important points. N-type extrinsic semiconductor can be created by the addition of the fifth group impurities to the intrinsic semiconductor. P-type extrinsic semiconductor can be created by the addition of the third group impurities to the intrinsic semiconductor. These fifth group impurities are nothing but you can take here phosphorus, arsenic, antimony. You can take them like fifth group impurities for the creation of the extrinsic semiconductors. Fifth group is nothing but these are having the valency electrons 5. That's why these are coming under the fifth group elements. And third group impurities means third group elements we have to take like boron, aluminum, gallium. Okay, and here valence electrons will be 3. In each boron atom, 3 valence electrons will be there. In each phosphorus atom, 5 valence electrons will be there. In the fifth group element, you can observe bismuth also. But bismuth cannot be treated like a fifth group impurity. Okay, bismuth we cannot able to use. Remember that point. Okay, then now we will see exactly how this N-type extrinsic semiconductor can be created. As I said earlier, fifth group impurities we have to add to the intrinsic semiconductor. Intrinsic means again you can take silicon. So I am taking silicon crystalline structure. So for the explanation purpose, we are taking just 9 elements, but actually it is a series of so many number of elements. So I am taking here silicon crystalline structure, it is an intrinsic semiconductor. So all are silicon atoms only. And we are interested in the outermost 4 electrons only. Each silicon atom will be in covalent bond with its neighboring 4 silicon atoms. To get stability in the outermost orbit, actually 8 electrons should be available. But each silicon atom is having 4 electrons only. Then how the stability is achieved means 4 more electrons it can able to get from the neighboring silicon 4 silicon atoms. It is sharing basis. Okay, so that all the silicon atoms will be stable. This is the process involved in the crystalline structure of the silicon. So what type of bonding is there among the silicon atoms means you need to tell covalent bond. It is based on the sharing of the electrons. So I am showing here just 4 valency electrons. Remaining are not required because those are available in the inner orbits only. So whatever the electrons I am taking now, these are the 4 valency electrons of this silicon. And now I am concentrating on this silicon atom. It is also having, this is nothing but covalent bond. This representation is covalent bond. It is also having its own 4 valency electrons. These 4 valency electrons are of this silicon atom. Similarly, we can able to extend the diagram. So for all the silicon atoms, I am representing their 4 outermost electrons. Like this I am representing. You concentrate on this silicon atom. So this silicon atom is having its own 4 valency electrons. And fifth valency electron we are getting from this silicon. Sixth electron is getting from this silicon atom. Seventh electron we are getting from this silicon atom. Eighth electron we are getting from this silicon atom. So this silicon atom is having the 4 covalent bonds 1, 2, 3, 4 from the neighboring 4 silicon atoms. So totally it is getting 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are there in the outermost star. So that we can tell it is getting the stability. So this is the situation available in the intrinsic semiconductor. It is about the intrinsic or pure silicon atomic structure, crystalline structure. Okay, now to get this n-type extrinsic semiconductor, what we need to do means we need to add the fifth group elements to this intrinsic semiconductor. Then what will happen, that is what we need to see. Okay, so now I am erasing this intrinsic because I am going to show about extrinsic, and I am removing this silicon also. So we are going to get now extrinsic by adding fifth group element like phosphorus. I am taking phosphorus, but phosphorus is the fifth group element. It is having 5 valency electrons. Out of 5 valency electrons of the phosphorus, out of 5 valence electrons of phosphorus, 4 are in covalent bond with 4 neighboring silicon atoms. You see here, it is phosphorus. Its own valence electrons are 5. 1, 2, 3, 4. And fifth one is not in the covalent bond. Fifth one is outside. This is the fifth electron. 1, 2, 3, 4. So out of 5, 4 are in covalent bonds, but fifth one is not in the covalent bond. Fifth one is loosely connected. Okay, fifth one is loosely connected. So compared to these 4 valence electrons of the phosphorus which are in covalent bonds, this fifth electron is loosely bounded. So removing this fifth electron is easy compared to removing these 4 bonded electrons, because these are in the covalent bonds, but it is not in the covalent bond. So with the little application of the temperature, with a little increment in the temperature, fifth electron can become free, but due to this one, hole cannot be created. This is a main important point here. Okay, because of this one, hole cannot be created. Why? To create the hole, it should be from the valency band. It should be from the covalent bond, otherwise. It should be from the covalent bond. So these 4 are there in the covalent bonds, but fifth one is not in the covalent bond. So that what we can able to tell here, this hole cannot be created, but free electron is created. In case of intrinsic semiconductor, how many number of free electrons are there? Same number of holes will be created. But here, without creation of the hole, one free electron is already created. Like this, for example, here I have discussed with respect to only one phosphorus atom. If I add 10 phosphorus atoms, then 10 fifth electrons will be there. 10 fifth electrons are loosely connected, loosely bounded. So those 10 fifth electrons can be easily make free electrons with the little application of the temperature. So 10 free electrons are generated without creation of single hole. And holes will be created when you increase the temperature up to 300 degrees Kelvin. Then all these bonded electrons will become free. So holes will be created. But in addition to that one, many free electrons are already there. That is why free electrons will be larger compared to holes in the n-type semiconductor. So we can able to tell n is equal to p in the intrinsic semiconductor, and we can able to tell n is greater than p in the extrinsic semiconductor. So that I can tell electrons are majority charge carriers in the n-type and holes are minority charge carriers in the n-type. Okay, and this analysis can be done for p-type semiconductors also. Okay, so p-type extrinsic semiconductor, as I said, third group elements are to be added. Third group elements are to be added to intrinsic. So same structure I am taking. First I am taking complete silicon, 9 silicon atoms for the explanation we are taking. And this structure can be repeated, it can be extended. So for the explanation purpose we are taking like this. So this is the pure silicon. So all atoms are silicon only. Now we are adding one boron atom. For example, third group element is nothing but boron you can take. It is having just 3 valency electrons. But actually here each silicon atom is having 4 covalent bonds with the 4 neighboring silicon atoms. So when you replace this one silicon with so here boron is there. Boron is having only 3 valency electrons. So it is the valency electron of the boron, it is another valency electron, it is the third valency electron of the boron. Here previously covalent bond is there. This electron is related to this silicon. But now here vacant space is available. To fill this one, there is no free electron for the, or there is no valence electron for the boron. So it is, this vacant space is there in the covalent bond only. So it is called hole. So this hole is created, but free electron is not created. So if you add 10 boron atoms, so 10 holes will be created like this. If you add 100 boron atoms, so 100 holes will be created like this without creation of the free electrons. That means here hole concentration is greater compared to electron concentration. If you increase the temperature, certain electrons will be created, certain free electrons will be created, but equal number of holes will also be created. But here already some holes have been created, so that P is greater than N. So this is analysis we have to do for the 3 semiconductors. So I am taking here semiconductor and the relation between N and P and majority, minority. So semiconductor, first one I am taking intrinsic only. Next one is N type extrinsic semiconductor. Next one is P type extrinsic semiconductor. So we know all these things. For the intrinsic semiconductor, the relation between N and P. So these two are same. So N is equal to P we have to take. And in case of N type semiconductor, N is greater than P. In case of P type semiconductor, N is less than P. That means here majority minority, it is not like that, because this free electron concentration is exactly equal to hole concentration. So nothing is majority, nothing is minority. But in case of this N type semiconductor, majority are free electrons. These are very, very important points. And minority means holes. Next, in case of P type semiconductor, majority are nothing but holes and minority are nothing but free electrons. Okay, so this table is very, very important, which is giving the information about the relation of N and P and which are minority and which are majority in case of the intrinsic, N type and P type semiconductors. So next topic is about continuity equation. So continuity equation is related to about currents. It is giving the relations related to currents only. So it is given by del dot J bar is equal to minus dou rho V by dou T. So if you observe this equation, del is nothing but vector differential operator. Del, it is called del vector differential operator. It is giving about all the 3 directions x, y, z. So you can simplify this one by taking in only one direction also, or 2 directions, or completely 3 directions. So it is differential operator generally, like dou by dou x, dou by dou y, dou by dou z. If you are restricted to only one direction like x, then dou j bar by dou x, like this you can do. Okay, so it is equal to minus dou rho v by dou t. So J is the current density, rho v is the volume charge density. So it is about charge only. So left side you have current term, right side you have charge, rate of change of charge because of dou by dou t. Rate of change of charge. So rate of change of charges is nothing but current only. So that is nothing but our continuity equation. Okay. Then we will compare silicon and germanium in various aspects. So silicon and germanium I am taking. So if you take atomic number, for silicon it is 14, for germanium it is 32. Okay, when you compare with respect to atomic number. Then if you take a mobility that is nothing but a mu. Mobility is indicated with mu. Mobility is there for the electrons and mobility is there for holes also. Mobility of the electrons is indicated with mu n, suffix is n, and mobility of the holes is indicated with the mu p. And for the silicon and for the germanium, how these mobility of the electrons and mobility of the holes are available, we have to know. So in case of the silicon, mobility of the holes is 500, and in case of the silicon, mobility of the electrons is 1300. Okay, and the related values with respect to germanium is given by 1800 and 3800. 1800 is the mobility of the holes in germanium. 3800 is the mobility of the electrons in the germanium. Okay, now we will see what is mobility. Mobility is relating the drift velocity and electric field, applied electric field. These two are actually directly proportional for the lower values of the applied electric field. So Vd is equal to, if you remove this one, you will get the mobility. So mobility is a constant. For the lower values of the applied electric field, the velocity is directly proportional to the applied electric field. So this is the relation. Then what are the units of mobility? That is also one of the important questions. So because it is the velocity measured in meters per second or centimeters per second, it is equal to mobility, we don't know, and this electric field is given by volts per meter or centimeter. As I have taken here centimeter, here also centimeter I have to take. So mobility units will be given by centimeter square by volt second. So very important this one. Okay, so mobility is the ability of the charge carriers, that may be electron, that may be hole, with that ability how it is moving. That is nothing but mobility. With the application of the electric field, velocity can be provided to the charge carriers. Velocity means movement. So the ability of that particular movement can be obtained because of the application of the electric field, that is given by this mobility concept. So in case of the silicon, mobility of the hole and electron are given by 500 centimeter square per volt second, 1300 centimeter square by volt second respectively. And in case of the germanium, 1800 and 3800. Okay. So by observing this one, we can able to tell the mobilities of the free electrons and holes are greater in case of the germanium compared to silicon. And now we can compare the intrinsic concentration also. Intrinsic concentration means you need to take the pure silicon atom without any doping concept. You need to take pure germanium without adding any impurities, that means without doping. Then how many number of electrons are created, free electrons, or how many number of holes are created is nothing but Ni. So Ni is nothing but N is equal to P only. Okay, for intrinsic concentration. Okay, so it is given by 1.5 into 10 power 10 silicon atoms or free electrons or holes per 1 centimeter cube, and it is 2.5 into 10 power 13 per centimeter cube. Per 1 centimeter cube, 1.5 into 10 power 10 free electrons or holes are available. It is 10 power 10. And 2.5 into 10 power 13 will be there per 1 centimeter cube in case of the germanium. And you can compare with respect to Eg also. Eg at 0 degrees Kelvin is given by Eg naught. Eg naught means energy gap at temperature is equal to 0 degrees Kelvin. In case of the silicon, it is 1.21. And in case of germanium, it is 0.783. And if you increase the temperature up to 300 degrees Kelvin, then Eg, we are representing just with Eg when temperature is 300 degrees Kelvin. So when you increase the temperature, this energy gap will be reduced to 1.1 from 1.21. And in this case, it is reduced to 0.72 from the 0.783. So this is the general comparison of the silicon and germanium. By observing all these values, you may think that germanium is better compared to silicon, because germanium atomic number is greater compared to silicon. Germanium mobility of the electrons is greater compared to that of silicon. Germanium holes mobility is greater compared to that of silicon. Germanium intrinsic concentration is also greater. It is required for the conduction purpose. Conductivity is directly proportional to this concentrations only. If you have more number of charge carriers, more charge carriers are moving is nothing but more conductivity can be possible. So by seeing these numbers itself, we can able to tell germanium can able to provide more conductivity compared to silicon, because silicon is having 1.5 into 10 power 10 per 1 centimeter cube, but it is having 2.5 into 10 power 13 per 1 centimeter cube. So intrinsic concentration is greater in case of the germanium, and energy gap must be low to get the more conductivity. We have seen the concept of the energy gap. If this energy gap is low, then only all the bounded electrons can able to jump into the conduction band very easily. So this jumping process can be very easy when this gap is very less. With a little application of the temperature, these bounded electrons can able to jump into the conduction band. So this is possible when this gap is low. So gap is low in case of the germanium only. So by seeing all these things, we can able to tell that it is looking like that germanium is better compared to silicon, but it is not true. Okay, why is silicon is better? Silicon is better compared to germanium. Why? What is the reason for this means? The first one is, you can tell silicon is more widely available, and silicon is cheaper one. Compared to these two reasons, you can able to tell another one, that is silicon is thermally stable. It is very, very important. Silicon is thermally stable. What is the meaning of this one? Further, when you are going to study about the p-n junction diode, you will get more clarity about this particular statement. Silicon is thermally stable means, thermally means temperature. When you increase the temperature or when you change the temperature, you should not get many changes in the performance of the devices which are fabricated using the silicon. You are changing the temperature. So this IC naught or I naught, simply I naught, reverse saturation current we can say, later we are going to see them. So this reverse saturation current should not be changed, it must have the stable. If it is not stable, temperature is changing. If it is not stable, it will affect the overall current also. Okay, then we can tell that is thermally unstable. But compared to germanium, it is stable. Silicon is stable. That is what we need to understand. Okay, compared to germanium, silicon is stable. This is very, very important reason to choose this particular silicon compared to germanium. Okay.